Right now, as you watch this, a small spacecraft is flying through the coldest, emptiest region humanity has ever reached. The temperature around it, nearly minus 270 degrees Celsius. That's just 1 degree above absolute zero, the theoretical point where all molecular motion stops, the point where matter itself gives up. And Voyager 1 has been out there for over 45 years. It launched in 1977. It has traveled more than 23 billion kilometers from Earth. It crossed the boundary of our solar system over a decade ago. And as of right now, it still works. It still sends signals. It still talks to us. How? How does a machine built in the 1970s survive the most hostile environment in the known universe for nearly half a century without freezing solid? The answer isn't simple, and it's more fascinating than you might expect. Because here's the thing. The real question isn't whether Voyager can survive the cold of space. The real question is whether you understand what cold in space actually means. When you step outside on a winter morning and feel the cold hit your face, something very specific is happening. Air molecules, billions of them, moving fast, are colliding with your skin. Each collision carries heat away from your body. The more collisions, the faster you lose heat. The faster you lose heat, the colder you feel. That's conduction. And it requires contact. It requires matter. Space has almost none. In the interstellar void, where Voyager 1 travels right now, there are roughly a few atoms per cubic centimeter. Compare that to the air in this room, around 10 billion molecules per cubic centimeter. The difference is almost incomprehensible. With so few particles to collide with, heat can barely conduct at all. There is no medium to rob warmth from a spacecraft the way winter air robs warmth from your face. So how does heat escape in space? Radiation. Every object with a temperature above absolute zero emits heat as infrared radiation, invisible light that travels outward in all directions. In space, that's the only way heat moves. And radiation is slow, gradual, manageable. Think of it this way. In a cold room, a cup of coffee cools quickly because air is constantly stealing heat from the ceramic. Put that same cup in a vacuum and it cools far more slowly, radiating heat outward like a dimming lamp. Voyager 1 is that cup of coffee, floating in a vacuum so deep that heat can only escape one way. That changes everything. The cold of deep space isn't aggressive. It doesn't attack. It simply waits for your heat to bleed away. And if you generate heat fast enough, you survive. Voyager doesn't have solar panels. That's not an accident. The engineers at NASA knew exactly where this spacecraft was going. At the distance of Jupiter, sunlight is already 25 times weaker than on Earth. At Saturn, even more. By the time Voyager crossed into interstellar space, solar panels would have been useless. Cold, dark, dead weight. So they chose something else. Plutonium-238. Voyager carries radioisotope thermoelectric generators, 3 of them. These devices work on a principle almost poetic in its simplicity. Plutonium-238 decays radioactively, and that decay releases heat. Constantly. Automatically. Without fuel, without combustion, without sunlight. That heat passes through thermoelectric converters, materials that generate electricity when one side is hot and the other is cold. No moving parts, no switches, no maintenance required. When Voyager launched in 1977, its RTGs produced around 470 watts of power, enough to power several light bulbs. Modest, but sufficient for a spacecraft designed to be ruthlessly efficient. But the RTGs do more than generate electricity. They generate heat. And in the cold of space, heat is survival. The warmth produced by the RTGs radiates through Voyager's systems, keeping electronics, cables, and instruments within operational temperature ranges. Even the electronics themselves, every circuit that fires, every calculation that runs, produces residual heat that contributes to keeping the spacecraft alive. It's a closed loop of warmth in the middle of an infinite freeze. But warmth alone isn't enough. You also have to keep it. Imagine wrapping something in a blanket so advanced it reflects heat back at itself. A blanket so thin it weighs almost nothing. a blanket designed not for comfort, but for survival at the edge of the solar system. That's what covers Voyager. Multi-layer insulation is a technology built from ultra-thin sheets of mylar and kapton, layered together with gaps of near vacuum between them. Each layer reflects infrared radiation. Each gap prevents conduction. Together, they create a thermal barrier that slows heat loss to a crawl. Voyager is wrapped in this material like a gift sealed against the universe. But here's the engineering challenge that most people don't consider. The problem wasn't just keeping Voyager warm far from the sun. The problem was keeping Voyager from overheating near the sun. In the early years of the mission, during the flybys of Jupiter and Saturn, the spacecraft was relatively close to our star. The RTGs were running at full power. The electronics were generating heat, and sunlight, while weaker than at Earth, was still a factor. Engineers had to design a thermal system that could handle both extremes, the warmth of the inner solar system and the deep freeze of interstellar space. A balance struck with layers of insulation, thermal louvers, and radiators that could vent excess heat when needed. It worked. Decades later, in temperatures approaching absolute zero, Voyager's core systems still operate within their design parameters. A thermos in the void, engineered to survive anything. In August 2012, something historic happened. Voyager 1 crossed the Heliopause. You may not know that word, but it describes one of the most important boundaries in our cosmic neighborhood. The Heliopause is the edge of the heliosphere, the vast bubble of solar wind and magnetic influence that our sun projects outward in all directions. Inside the heliosphere, the sun's particles flow and interact with everything. Outside it, the sun's reach ends. Voyager 1 became the first human-made object to cross that line, to enter true interstellar space. The environment changed immediately. The solar wind, a constant stream of charged particles from the sun, stopped. The magnetic field around the spacecraft shifted. The radiation environment became dominated, not by our sun, but by the rest of the galaxy, and the temperature of the surrounding medium dropped even further. In the heliosphere, the tenuous plasma can be surprisingly hot, millions of degrees in some regions, though so sparse it transfers almost no heat to anything. Beyond the heliopause, the interstellar medium is colder and denser, still impossibly thin by Earth standards, but different. Voyager crossed into this region and kept going. The RTGs kept producing heat. The MLI kept trapping it. The thermoelectric generators kept converting it into power. A machine built in California in the 1970s, operating in a region of space no human instrument had ever reached, functioning exactly as designed. There is something almost defiant about it. But nothing lasts forever. Plutonium-238 has a half-life of about 88 years. That means every 88 years, half of the remaining plutonium decays into lead, and the heat output drops by half. The process is slow, but it's relentless. Since 1977, Voyager's RTGs have lost roughly 40% of their original power output. What started at 470 watts now produces somewhere around 250 to 260 watts, and it drops by approximately 4 watts every year. NASA has been managing this decline carefully, systematically, ruthlessly. Over the decades, they have powered down systems one by one to keep the most critical instruments alive. Cameras, long since off. Certain science instruments, deactivated. Heaters for non-essential components, switched off, allowing some parts of the spacecraft to cool and partially freeze, as long as the core keeps functioning. It's a managed death, slow, deliberate, and inevitable. Current estimates suggest the last science instruments will go silent somewhere between 2025 and 2030. Some may already be offline by the time you watch this, and when the final systems lose power, when there is no more electricity to run the transmitter, no more warmth to protect the circuits, Voyager will begin to truly freeze, not because space suddenly became colder, but because the source of heat is gone. The insulation will still be there, the mylar and kapton still wrapped around the frame, but they can only slow the inevitable. Without the RTGs, the heat bleeds away into the void, slowly at first, then completely. The death of Voyager won't be an explosion. It won't be a collision or a failure or a dramatic final transmission. It will be silence. One instrument going dark, then another, then the transmitter itself. One last signal crossing 25 billion kilometers of empty space, taking over 21 hours to reach Earth, and then nothing, just silence. But here is what stops you cold when you really think about it. Voyager doesn't stop. In space, there is no friction, no air resistance, no force to slow a moving object down. Newton's first law, applied at cosmic scale: an object in motion stays in motion. Voyager 1 is currently traveling at approximately 17 kilometers per second. That's over 61,000 kilometers per hour. And when its last system goes dark, when the final signal fades, when the spacecraft is nothing more than frozen metal and exhausted plutonium drifting in the interstellar medium, it will still be going 17 kilometers per second. In roughly 40,000 years, Voyager 1 will make a close approach to a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. Not a collision, just a pass. The closest it will come to another star since leaving our solar system. No one alive today will know when it happens. There will be no signal to confirm it, no instrument to record it. Just a frozen spacecraft, drifting past a distant star in the darkness, carrying a golden record with the sounds and images of a civilization that existed, briefly, on a small planet around an average star. A fossil, traveling forever. Think about what that means. Voyager was never designed to last this long. It was designed to go, to reach Jupiter, Saturn, the edge of the solar system, and keep going. The durability wasn't the goal, the journey was. And yet here we are, nearly 50 years later, still listening, still receiving data from a machine smaller than a school bus, operating on less power than a light bulb, in conditions that would destroy almost anything humanity has ever built. It didn't freeze because we understood the cold, not just the temperature, but what cold in space actually means. The absence of conduction, the slowness of radiation, the way heat behaves when there is almost nothing around to take it. We gave Voyager a heartbeat of plutonium and wrapped it in the thinnest armor imaginable. And it flew. It's still flying. When the last signal comes, and it will come, probably within this decade, what exactly are we losing? A spacecraft? A science instrument? A piece of 1970s engineering? Or the last physical proof that a small, curious species looked up at the stars, built the best thing it knew how to build, pointed it at the unknown, and let it go? Maybe the answer is all of the above. Maybe that's enough. If this made you think about the universe differently, subscribe. And tell me in the comments, when Voyager finally goes silent, what do you think humanity should do next?